Hello, my name is Nedumpurath, and this is my Physics Lab 1 video on constant velocity. The objective was to use the momentum principle to model the movement of a non-accelerating object using GlowScript. The momentum principle states that force is equal to the rate of change of momentum, which is approximately equal to mass times the average rate of change of velocity, if the mass is constant. A trend line was created using data obtained from a tracker site, and using the rate of change of this trend line, which serves as the average velocity, the future position of the ball can then be predicted. So the experiment, as you just saw, consisted of rolling a soccer ball across a flat floor, and the initial position is just the first frame of the video, and the x and y axes were arbitrarily chosen to be the center of the ball. So what this means is that the initial position of the ball is 0, 0. Also, since the positive axis was chosen to be towards the right, that means that both the positions are increasing. Positively, and the velocity is also positive. If the positive axis was chosen to be to the left, the results will be the same, but the velocity and the position numbers will be multiplied by -1. For instance, as you can see on this graph here, instead of the end position being around 1.5 meters, it would be -1.5 meters. A trend line was used rather than an average rate of change calculation to better account for inaccuracies. And because as we're arbitrarily selecting the center of the ball in each frame, we're going to end up with some manual errors and also just errors from the tracker website itself. So during the lab, the motion of the ball was relatively constant and point masses were tracked quite accurately. However, the trend line correlates to the data very well with an R-squared value of 0.9942. There was some inaccuracy at the beginning and the end, as you can see, and this is due to the fact that the experimental position graph is concave down, which means that there's a decelerating effect in place. So what this means is that unlike the assumption in our model that there's no net force, there is actually a force acting on this ball, which is most likely friction. So this is the main limitation of this model. It assumes that there's zero friction, but however, as in any case in real life, there is friction. Seen here is the GlowScript code for the model. So the first thing that was done was that the mass and radius of the balls were changed to match the actual measurements, so 0.44 kilograms and 0.11 meters in radius. Then the initial position and velocity vectors that were derived from the trend line were then reflected in the code. So as you can see, the position reads 0.88 meters, 0, 0, and this matches what was in the trend line. Then in the calculation loop, the time interval was changed to 0.133, which matches the clipped video at the end. And also, the update lines for the velocity and position were changed to match the kinematic equations that are in the bottom right. So this is the GlowScript model in action. It very simply shows the ball moving. So overall, the model was able to quite accurately reflect the movement of the ball during this interval. However, it was slightly inaccurate during the beginning and the end of the time interval. And as I mentioned earlier, the actual observational graph was concave down, indicating that there is a decelerating force acting on the object. As time passes, thus the ball is then moving with less velocity. The reason for this is that the net force is not zero, and that there is friction and air resistance, most likely, that are resulting in deceleration. Also, it's not possible to actually know exactly how many forces are combining to add up to this net force, because there's an unknowable number of interactions on this given object. Electrostatic interactions with the air, gravitational forces between me and the ball or the table and the ball, and so it's impossible for us to actually know exactly what's happening to the ball. So in the future, I would like to record the ball's movement along a longer time interval and distance in order to see how well a linear prediction would hold up. For example, if I saw that there's a lot of deviation, that it's really decelerating and is very concave down, I might want to use a nonlinear regression of some sort. So recording for a longer time interval and distance would allow me to see the role of friction. Also, I might want to use a smoother ball, like a bowling ball, that would exhibit less deceleration due to friction. Because the soccer ball is kind of lumpy and not smooth, it's going to be exposed to more friction than a smooth ball would be. So that was my project. Thanks for listening to my video, and I hope you have a nice day.